Hello, welcome back to Atoms and Sporks, and today we're going to continue our discussion of the applications of nanoplasmonics. And I'm going to 100% assume you watched the last video here, which was about applications for localized heating in chemistry and in color displays. In this video, we're going to talk about applications in sensing and basic science. Just to maybe refresh your memory a bit, the key properties of nanoplasmonic particles was that when they are illuminated by light, 1. They act like lightning rods or nanoantennae and boost or divert the electromagnetic field of the light and channel it into a small area around the particle. 2. This enhancement has a certain specific resonant frequency where it is especially powerful. And 3. This resonant frequency is tunable and based on the shape of the particle and on the environment surrounding the particle. Also remember that I'm saving a physics discussion of why they have these properties for our next video. But for now, let's start a discussion by talking about surface-enhanced Raman spectroscopy, or SERS. Raman spectroscopy, by the way, being the tastiest of spectroscopies. Spectroscopy, in the most vague and broadest sense, can be described as the study of the interaction between matter and light. Now, that's maybe not the most illuminating definition, but if you recall, we described nanoplasmonics as a means of enhancing light-matter interaction. So you can see right off the bat, if one is about studying light-matter interaction and the other enhances light-matter interaction, why these two fields, nanoplasmonics and spectroscopy, might be good friends. In a spectroscopic experiment, you basically shine light on a sample, and that light is then used by the sample to do stuff. And then you get some light that comes out of the sample, which you then measure. And based on how the incident and outgoing spectrums of light are different, you can tell things about the thing you're studying. Now, when I say the light is used to do stuff, I mean like maybe it's absorbed to transition an electron between states. In that case, the outgoing light will then be missing certain wavelengths that correspond to those electronic transitions. I learn about what materials and molecules are in the sample by what's missing in the outgoing light. Another thing that can happen is that a photon is only partially absorbed to, say, vibrate some molecule, and thus only part of the energy of a photon is used, and the resulting photon that comes out has been what we call redshifted. So light of one color went in, and what came out was a different redder color, and the amount that the color has shifted tells you about what's in the sample, and the environment it's in. It is this kind of so-called inelastic scattering of light that Raman spectroscopy is concerned with. Raman spectroscopy is used a lot in biology. Part of the reason for this is because water actually has a very poor response to this kind of probing, and thus it's very good at getting information about the things in a biological sample that aren't water. And that's generally the stuff you actually care about. Things like the presence and abundances of various biological molecules. Proteins, viruses, DNA, hormones, stuff like that. So Raman's ability to ignore water lets you get very good information about the good stuff. Now, the problem with Raman spectroscopy is that the kind of transitions it's concerned with, these inelastic scattering events of light, are very, very unlikely. This means that the Raman signal is very, very hard to detect. Well, it's nanoplasmonics to the rescue. There's two ways you can do this. The easiest way is to simply mix in some of these metal nanoparticles into a biological sample. The other and more common way is to actually make a rough metallic surface, where you either have affixed nanoparticles, or the surface is metal that's just so jagged and rough that you get particle-like jagged edges and points. This, by the way, is actually how surface-enhanced Raman spectroscopy was discovered. In 1974, Martin Fleischmann and colleagues basically just noticed that if you did Raman spectroscopy on a rough silver substrate, it worked way better. Originally, they attributed this to just the fact that when you have a jagged surface, there's more surface area of the silver exposed. And it was a reasonable conclusion, except how much was the Raman spectroscopy improved? Was it twice as good? 5 times better? 10 times better? No, it was 1,000,000 times better. It didn't take people long to realize that there was no way that that was just about more surface area, and people soon caught on to these exciting nanoplasmonic effects at play. And once we understand the physics of something, that's when we can start engineering things to maximize the effect. Nowadays, people see Raman signals enhanced by factors of tens or hundreds of trillions. That is insane, and it means it's literally 1,000,000 times better than when it was first detected. How's that for progress? In fact, that's such an enormous enhancement that one could potentially identify the presence of even a single molecule of a substance with a strong Raman signature within a sample. It's pretty easy to see what the applications of this are. Whether it's testing for toxins in water, or forensics and criminal investigation, or impurities in manufacturing processes, there's a lot you can do. And there's actually one other huge place, but I'll get to that in a second. But first, let me also point out that you can actually take this show on the road. Rather than having some sample poured onto a nanoplasmonic surface, or with nanoparticles mixed in with it, you can take a single nanosphere and affix it to the tip of basically a record needle. You can then run this record needle over a sample while illuminating it with a laser and obtain precise information about the chemistry and structure of the very small region immediately under the needle. In other words, this so-called tip-enhanced Raman spectroscopy, or TERS, allows you to spatially scan and locate specific molecules or chemistry on a surface. In fact, it's actually a rule in optics that you generally can't use light to resolve features that are much smaller than the wavelength of light being used. This means that you can't use visible light to optically resolve features that are smaller than a few hundred nanometers, because visible light runs from 400 to 700 nanometers. However, with tip-resolved Raman spectroscopy, you can resolve features that are 10 times smaller than that, because the nanoparticle on the tip only gives information about a very, very small region around it, because that's the only area where the laser's electric field is enhanced. But Raman spectroscopy is far from the only way you can use nanoplasmonics for science and sensing. Another important way you can use this is by coating your nanoparticles with some biological molecule that only binds with a very specific other biological molecule. Any molecule you basically glue to the nanoparticle is then called a ligand, and it is a molecule that is looking to latch on to some other very specific molecule called the analyte, the one being analyzed. Initially, when there are no analytes present, this nanoparticle will have its signature resonant frequency, which can be easily identified. However, once the analyte attaches itself to the ligand, and thus starts filling the space around the nanoparticle, the environment has changed. And as we said, when the medium surrounding the nanoparticle changes, this resonant frequency shifts downwards. And this is something you can very clearly detect. In fact, often you don't even need some super fancy machine, you can just see it by eye. A prime example of where this can be seen is home pregnancy tests which use so-called immunochromatographic assays. In a pregnancy test, you're trying to detect the presence of a hormone called HCG in a woman's urine. And no, I'm not going to say what HCG stands for. You're lucky I made a go at attempting to pronounce immunochromatographic assays. But basically, you have some antibody affixed to a strip, which will bind to HCG, and then you also have gold nanoparticles that are also coated with a ligand that attaches to HCG. So if HCG is present, your nanoparticles get bound to the strip region with the HCG in the middle, and because their environment has changed, their resonant frequency shifts from green to red, and the color of the strip changes. Nanoplasmonic-based diagnostic tests like this have been shown to be able to produce visible color changes when even as little as an attogram, that's a 1,000,000 trillionth of a gram of the analyte, is present in a sample. It can be used for diagnosing things like HIV, or different types of cancer, or hormonal conditions, or 100 other things. I actually think it's important to really think about the potential for this. You're getting a visible color shift from even trace amounts of a compound. There's potential here, for example, to create implantable diabetes sensors, something that gives a diabetic continuous, real-time information about their body's glucose levels, just by glancing at the color of the implant. No strict regimen of regular blood tests, just something you can glance down at and at any time go, oh, it's getting a little red, time for a shot. Or imagine at a security checkpoint in an airport or the like, that there's just like this blue strip, this ominous blue strip, and if you ever notice that strip changes to red, then there's a certain concentration of gunpowder or explosive residue in the air, and you can instantly see it. I mean, there are 100 ways you can imagine using such a compound-specific nanoplasmonic strip that produces such an obvious visible change in the presence of such a tiny quantity of a compound. Okay, so hopefully after 2 freaking videos, that gives you at least some idea of the applications of nanoplasmonic technology. In fact, I literally only broached half the subject. Everything we've talked about is related to what are called localized surface plasmonic resonances, or LSPR. It's the enhancement effect in the neighborhood of some small nanoparticle. There's actually a whole other side of plasmonics related to what are called surface plasmon polaritons, or SPPs, that have a whole other set of applications, like an entire new way of implementing computing technology. But I'm going to save surface plasmon polaritonics for a different tour of physics video, some point in the future. Regardless, hopefully you now have an appreciation for the applications of this field. And of course, I never said why these metal nanoparticles behave this way. I never once discussed the physics of it. And that will be the topic of our next video. The physics of nanoplasmonics. Hope to see you there. Have a good one.